Hi, hello, welcome to Mickey Tiki. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students and subscribers for their continuous support and encouragement. Today's topic of interest is thermodynamic cycles. In thermodynamics, we are having nearly a 10 number of cycles. One cycle, a thermodynamic cycle, comprises of different kinds of processes where the input and output point, the initial and final point, are come in a single point. The cycle must be closed. The process must be a closed loop. That is why it is called as a cycle. If we are having a different processes, means if I say this is a constant volume, this is a constant pressure, and a isentropic compression and a constant pressure cycle, means if these are all the processes, if I say this is process 1, 2, 3, 4, if this four process is comprises of a cycle, so this is a closed loop, this is called as a cycle. Here the work done, that is some work done is there. Number of cycles, number of processes are combined together and perform and work. So that is called as a cycle. That is called thermodynamic cycle. We are having nearly 10 different types of a thermodynamic cycle in nature that we are going to discuss in the next slide. First, it is an ideal cycle. If I say ideal cycle, you will get a reminder of Carnot cycle. Here we are going to discuss the PV diagrams only, the pressure in y-axis and volume in x-axis. Volume is an independent variable, pressure is an dependent variable. The cycle starts with the isothermal compression and adiabatic heat addition, isothermal expansion and adiabatic heat rejection. So this is the processes where the Carnot cycle, we can say, we can anyway we can start it. I can start from here. It is an isothermal expansion, adiabatic heat rejection and isothermal compression and adiabatic heat addition. So here it is heat is added and here it is heat is rejected, I can say. So this is how the Carnot cycle is being defined. So this is an ideal cycle, ideal heat engine cycle. So this is the cycle where we are going to compare the efficiencies of Otto, diesel and dual cycle with this Carnot cycle. So this Carnot cycle is called air standard cycle. So air standard cycle. So heat engines are compared with this Carnot cycle. The Carnot cycle, the how we can maximize the efficiencies, means the effective method of increasing the efficiency is reduce the lower temperature or reduce the sink temperature. If we this Carnot cycle is does not depends on the gas, it is depends on the temperatures alone. If we increase the peak temperature, we can get more efficiency, or we can decrease the uh, lower temperature, we get more efficiency. The efficiency is always less than 100 percentage. You can assume that the ratio the can assure that the efficiency of any cycle is less than 100 percentage. The efficiency is same for all reversible engines with the same temperature limits. All the ideal cycles are depends on the temperature limits. It does not depends on working fluid. So You can notice this. This is an Carnot cycle is an ideal cycle. Carnot cycle is an ideal cycle for engines. Okay. And next one is the Stirling cycle. So it is an important and interesting cycle where the constant volume is coming together since it is an ideal cycle. So this is an ideal cycle for the gas turbines. So ideal cycle for the gas turbines. Uh, and it is working with isochoric cooling and heating, that is constant volume heat addition as well as constant volume heat rejection. Here I go with the isothermal compression and isochoric heat rejection and isothermal heat rejection and isochoric heating process. Like this, the process is being convected. Next is an Erection cycle. So this Erection cycle, it is a vapor power cycle. It is again an ideal cycle for vapor power systems. Here, this cycle is a constant pressure cycle. Ideal cycle, but it is a constant pressure cycle. So here I go with isothermal compression, constant pressure heat addition, isothermal heat rejection, and constant pressure heat rejection. Like this, it can go. And next is the Otto cycle. So it is an actual cycle. It is an actual cycle of a heat engine. Most of the SI engines or petrol engines are working in an Otto cycle. So Otto cycle, it is having a constant volume of heat addition as well as constant volume heat rejection, you can say. In generally, all two-stroke and four-stroke petrol engines are following this Otto cycle. So here also volume in x-axis and pressure in y-axis. Here you can get the intake and exhaust stroke. This is called as a pumping cycle. So this line is called as a pumping cycle. So after pumping, once the gas in, what we can do, we do a compression process. The compression process follows adiabatic process. So adiabatic compression and a constant volume heat addition and adiabatic expansion and a constant volume heat rejection. So here this is an intake stroke, compression stroke, combustion stroke, this is power stroke, and this is heat rejection and the exhaust stroke. So this is a constant volume cycle. So this area under the PV diagram is called work done. So the area under PV diagram, it is called as an work done of the process. Next is a diesel cycle. All the combustion ignition engines, that is diesel engines, are following this diesel cycle. It is also a heat engine cycle. So Otto cycle and diesel cycles are actual cycles. We are using these actual cycles. This you have to remember. And here also the pumping cycle is there. After pumping, adiabatic compression, constant pressure heat addition, adiabatic heat expansion, and constant volume heat rejection, constant volume heat rejection. So here you can notice this, the compression process is more than the expansion process. Here we have two things. One is compression ratio and cutoff ratio is coming picture in diesel engines. The adiabatic compression, the compression process happens constant pressure heat addition by means of a fuel injector inside the engine's combustion chamber. It gets burned. So constant pressure only, the heat is being added. After that, the expansion stroke, and it goes out in the exhaust stroke. Next is a dual cycle. all the high speed engines are following this dual cycle. This is also an actual cycle where heat addition is done twice. One is in constant volume and a constant pressure. So it is also used in actual engines. So pumping cycle is there, so inlet and exhaust stroke is being happen, and adiabatic compression process, and first heat addition is constant volume and second heat addition is at constant pressure, and adiabatic expansion and uh, constant volume heat rejection. If you can see in actual cycle, whether it is an Otto or diesel or dual cycle, the heat rejection is takes place in constant volume. Heat rejection is takes place in the constant volume. Compression in adiabatic, expansion in adiabatic, whereas heat addition is being different. If I said if my heat is added at constant volume, it is an Otto cycle. If it is in constant pressure, it is a diesel cycle. If it is a dual cycle, both come together. So diesel cycle, dual cycle is a compresses of Otto as well as diesel cycle. So heat rejection, heat addition is been in twice in dual cycle. The similar to the diesel cycle, the compression process is more than the expansion process. Compression is more than the expansion. At the same compression ratio, if I say the compression ratio is constant, the efficiency of Otto is more than efficiency of dual. It is dual is more than efficiency of diesel cycle. If I said this is a relation, you have to remember that at constant compression ratio, at the compression at the same compression ratio, Otto cycle will produce a more efficiency than dual and diesel cycle. And the same pressure ratio, at the same maximum pressure, the diesel cycle produce more efficiency than dual cycle. It is more efficiency than Otto cycle. So this relation you have to remember. For maximum pressure in terms, diesel cycle produce more efficiency. If maximum compression ratio I said, the Otto cycle will produce more efficiency. Next is an actual cycle for gas turbines. This is none other than Brayton cycle. Brayton cycle are also called as a Joule cycle, where the pressure is being constant. Heat addition and heat rejection is takes place in constant pressure process. Here, these cycles are used in gas turbine power plants. This is also an actual cycle used in gas turbine power plants. So here, see, it is a gas turbine. The expansion ratio is more than compression ratio. The expansion ratio is more than compression ratio. This you have to remember. The combustor will add the heat and heat rejection to the atmosphere. The inlet and the compressor is takes place by means of an isentropic process, and turbine in the expansion turbine or nozzle, both are the expansion device. It is takes place in isentropic expansion, where heat addition in combustor takes place at constant pressure and heat rejection to the atmosphere takes place at constant pressure. So this you have to remember, the Brayton cycle. And next is an Atkinson cycle. This is a one and only cycle where the heat addition is at constant volume, heat rejection is at constant pressure. This Atkinson cycle is also being used in heat engines. Nowadays, the modern heat engines and variable valve timing engines are using this Atkinson cycle, where the compression process is less than the expansion process. The expansion process is being extended for to make the constant volume rejection to constant pressure rejection. So this is the special case in Atkinson cycle. So it is a constant volume cycle. It is a heat added is constant volume, heat rejection is takes place at constant pressure, where adiabatic compression is been happen and as well as adiabatic power expansion is been happen. So this you have to remember. Atkinson cycle means heat is added at constant volume, rejected at constant pressure. So this you have to remember. Next is an actual cycle for pulse jet engines. Pulse jet engines linear cycle. This is a special case of a cycle. In all the cycle we are having the processes or four or five processes we are going to discuss, where this linear cycle comprises of only three processes. One is constant pressure cycle, constant volume cycle, and isentropic cycle. So constant pressure heat addition, isentropic expansion, constant constant volume heat addition, isentropic expansion, and constant pressure heat rejection is being happen. So this is a pulse jet cycle. So it is a closed loop cycle. It is a closed cycle. So this you have to remember. Next is an Rankine cycle. It is also an actual cycle for a vapor power cycle. A vapor power cycle. Ideal cycle is an Erection cycle, whereas actual cycle is a Rankine cycle. Most of the refrigeration is taken, refrigeration of the air conditioning process or done by means of the Rankine cycle. So vapor power cycle, it is also a very important cycle. So here the constant thermal isothermal compression, adiabatic expansion, isothermal expansion, and constant pressure heat addition is been happen. So first one, isothermal expansion, adiabatic expansion, and isothermal compression and constant pressure heat addition. So like that it has been go. So this is the summary of the cycles. So as I said, ideal cycle it is Carnot cycle, temperature remains constant. Stirling cycle, volume remains constant. Erection cycle, pressure remains constant. Actual cycle or gas power cycles, that is heat engine cycles. Otto cycle means the heat addition volume is constant. Diesel cycle pressure is constant. Dual cycle volume constant, also pressure is constant. For gas turbine cycles, Brayton cycle or Joule cycle, pressure remains constant. Atkinson cycle, volume remains constant. For pulse jet engine, heat addition is done by constant volume process. And similarly, actual cycle for vapor power cycles, it is a Rankine cycle, heat addition by constant pressure. So this is all about the different types of cycles used in the thermodynamics. So with this I conclude today's session. If you have any doubts, please let me know in the comment section and I will put another video for clarifying your doubts. So until bye bye from Santhosh. Thank you for patient listening.